Let's have a look at electron arrangement and energy levels within atoms. Now, as we've looked at before, we've got a general model that we can use for the structure of an atom. And within the centre of that atom is what we call the nucleus, and the nucleus contains the protons and neutrons. We also have an electron cloud surrounding that nucleus. Now, whilst those are important parts and they determine our elements and things like that, it's actually the electron cloud that gives us our properties for each element. So we start with the premise of the positive protons should attract, being of larger mass, should attract the negatively charged electrons simply through that electrostatic attraction. But this doesn't happen. So why doesn't it happen? Well, it must be something to do with the energy of the electrons. In order for them to stay out at that distance within the cloud and not in the nucleus, they must contain energy. So if we start with that premise, and this was done 100, 150 years ago, we must also say that electrons possess that energy. Now, it turns out that they possess energy in discrete levels or discrete packets. And we call these levels of energy first, second, third, fourth, fifth, and so on, energy levels. Now, if we were to plot the energy of each level, we'd find that the first level contains the lowest energy. The second level would have the next highest, etc. like that, until we get out to an infinite number of levels, and that would contain the most energy and possibly enough energy to leave the atom. So only a certain number of electrons can exist in a given level. Otherwise it becomes too filled with negative charge, they repel each other, and the atom could break down. So we assign each level the term n. So n of the first level would have an n equal 1, 2 for the second level, 3 for the third, and we define the number of electrons that can fit within each level as 2n squared, where n is obviously the energy level. So let's have a look at how many electrons can fit in each level. For our first energy level, 2n squared, where n equals 1, we can fit a maximum of 2 electrons in there. For our second energy level, 2n squared, so 2 squared times 2 gives us 8 maximum electrons. The third level, 3 squared times 2 gives us 18 maximum electrons in the third level. Where n is 4, we've got 4 squared is 16 times 2 gives us the 32. And for our fifth level, 5 squared times 2 gives us 50 electrons maximum in that level. And obviously we can keep moving out theoretically to a very large number. Now, to determine our electron arrangement, and therefore what influences physical properties of atoms, we need some way of filling these electrons up. And they fill from the lowest energy level first. And that's the one that's closest to the nucleus. So we fill our electrons first. So that means we can have a maximum of 2 electrons in this level. Once we get more than 2, we shift up to the next energy level. And we keep doing that as we fill. So let's take some examples. And we'll draw the electron configuration as we go. Hydrogen with 1 electron, we represent with the 1 in the first energy level. Helium has 2 electrons, they also go in the first energy level. We then move up to lithium. We fill the first energy level with our 2, but now we've reached our maximum. So our third electron must fit in our second energy level. So we represent the electron arrangement for lithium as 2, 1. We move on to beryllium. 2 in the first, 2 leftover electrons, so it'll be 2, 2. And we can then move on to boron. We get 2 in the first level and 3 in the second level. We then move all the way to neon. 2 in the first level, 8 in the second level. It has 8 electrons. So we've now filled the second energy level as well. So for sodium, which is has atomic number 11, we've got 2 in the first level, maximum, 2 in the second level, maximum, So we've got to have our 11th electron in the third energy level. And then obviously we can move on to magnesium, being element number 12, will be 2, 8 and 2 electrons in that outer energy level. So this particular structure here, or how we represent it, is called our electron configuration, and we can do that for any element. Now, if we keep moving out, we get to argon as number 18. We get 2 in the first, 8 in the second, 8 in the third. Now, I've put this little box around because we will come to it in a second. Our next element, number 19, is potassium. Now, we would expect its structure to be 2, 8, and then 9 in the third, because we can have a maximum of 18 electrons in the third energy level. However, what we actually see in potassium is 2 in the first, 8 in the second, 8 in the third, instead of the 9, and 1 in the fourth energy level. Similarly, calcium has 2, 8, 8. We'd expect it to be 2, 8, 10, because there's 18 maximum here. But what we see is 2, 8, 8, 2. How does this occur? Well, it turns out that the electron configuration 2881 for potassium is more stable due to the possible interactions of having 9 electrons here rather than the 2881. Now that's a bit more complex chemistry, and we don't need to go into that at this stage. However, we can keep moving down. We get scandium, 2, 8, if we fill now, we go 2, 8, 8, and then we move across to 2 here for our calcium. After the calcium, after we've put 2 in here, we actually go back in scandium and start filling the third energy level. So for scandium, we get 2, 8, 9, 2, and then we can keep travelling across. So zinc would be 2, 8, 18, 2. So we've now filled the third energy level. Once we get to that, we get gallium, which is 2, 8, 18 once again, and we start filling the fourth energy level. And we go up to krypton, 2, 8, 18, 8. So we would expect our next element, rubidium, to be 2, 8, 18, 9, but we actually see, instead of being the 9 here, we start filling the fifth energy level, and we put a 1 in there. So that can create some confusion. However, if we look at our periodic table, and we look firstly at our alkali metals, we notice that for potassium, for sodium, for lithium, and to some extent for hydrogen, they all have a maximum of 1 electron in the energy level that is the furthest out with electrons in it. So they have that common property. Our alkaline earth metals all have 2 in the outer energy level where they've got electrons. Our halogens on the far right hand side all end in 7. So on the previous slide I gave us, actually we didn't do one, but our halogens would end in 7. And at the far right hand side, with the exception of helium, all of our noble gases have 8 in there. So what does that mean? Well, if we think on the far right hand side, we end in 8, our noble gases are very stable, they're not reactive. So what we can draw, or the conclusion that we can draw from that, is that this particular structure with 8 electrons in the furthest most energy level containing electrons is actually a very stable structure. So if we're to look at this and draw a conclusion about energy levels and structure of energy levels, we can say the number of electrons in the outer energy level, or what we call the shell, determines the chemical properties of an atom. And that's why our alkali metals all react in a similar way, because they have 1 electron in their outer shell. Our alkali earth metals, similarly, our halogens in a similar way, and our noble gases, which are unreactive, all have the same number of electrons in their outer shell as well.